Welcome to a story about a world you think you know. It is the ground beneath your feet, the air you breathe, the familiar horizon that greets you each morning. As we begin this journey together, you are part of a vast audience scattered across the globe, listening at all hours of the day and night. We invite you to leave a comment, telling us where in the world you are and what time it is for you as you listen. And if you enjoy exploring the hidden narratives of our universe, please subscribe so you'll be notified when we release new stories. This world, our Earth, is a place of such profound strangeness and epic history that its everyday familiarity is perhaps its greatest illusion. It is a story of fire and ice, of cataclysm and creation, of the relentless, patient forces that have shaped a planet, and the delicate, improbable spark of life that has taken root upon it. To truly understand this story, we must shed our human scale, our sense of the immediate, and learn to see our home not as a static landscape, but as a dynamic and ever-changing character in a cosmic drama that has been unfolding for billions of years. Our journey begins not on the ground, but in the vast, silent theater of space, where our world reveals itself as the third planet from the Sun, a delicate sphere suspended in the cosmic dark. From this vantage point, its most striking feature is an overwhelming, vibrant blue, a color that speaks of its unique character within our solar system. That overwhelming blue is no illusion. More than 70% of the Earth's surface is covered by water, a liquid ocean that distinguishes it from its rocky neighbors. This abundance of water is the crucible of life, the engine of our climate, and the reason our world appears as a shimmering, marbled jewel against the blackness. This seemingly perfect sphere, however, conceals a subtle deviation from true spherical geometry. The relentless spin of our planet on its axis, a constant rotation that defines our days and nights, creates a centrifugal force that has shaped its very form over billions of years. This force causes the world to bulge slightly at its midsection, a phenomenon that transforms the planet into what is properly known as an oblate spheroid. The diameter at the equator is about 43 kilometers, or roughly 27 miles, greater than the pole-to-pole diameter. This idea was first theorized by the brilliant mind of Isaac Newton in the 17th century, who reasoned that a rotating, fluid body would naturally distort in this manner. This equatorial bulge, a consequence of the planet's spin, has a curious effect on the force of gravity, the invisible tether that binds everything to its surface. Because of this shape, the force of gravity is not uniform across the entire planet. A person standing at the equator is slightly farther from the planet's center of mass than a person standing at one of the poles. Compounded by the slight outward fling from the rotation itself, this means you would weigh fractionally less at the equator. The difference is minute, a variance of less than 1%. but it is real. A subtle reminder of the complex physical forces at play on our dynamic world. That rotation, the very rhythm of our lives, has not always been constant. The length of a day on Earth is gradually, almost imperceptibly, getting longer. When our world was in its turbulent infancy, a full rotation took a mere 6 hours, resulting in a dizzying cycle of dawn and dusk. The slowing is a direct result of the gravitational dance with our moon. The moon's pull creates the ocean tides, vast bulges of water that are dragged across the planet's surface. This tidal friction acts as a powerful brake, slowly bleeding the planet of its rotational energy and lengthening our day by a few milliseconds each century. This is a process that has been unfolding over an immense timescale, a history that stretches back approximately 4.5 billion years. This staggering age was not always known to us. Its discovery is a story of profound scientific detective work. For centuries, the age of the Earth was a matter of theological and philosophical debate, with estimates ranging from a few thousand to millions of years. The true figure was unlocked only in the mid-20th century through a technique called radiometric dating, which measures the decay of radioactive isotopes within the planet's oldest materials. It was the painstaking work of geochemist Claire Patterson, analyzing lead isotopes from the Canyon Diablo meteorite, which fell to Earth 50,000 years ago, that finally pinned down our planet's true age with remarkable accuracy, revealing a history far deeper and more epic than had ever been imagined. Beneath this ancient surface, a furnace rages. The Earth's core, a churning sphere of molten iron and nickel, as hot as the surface of the sun, generates a powerful, invisible force field, the magnetosphere. This magnetic field acts as a planetary shield, a silent guardian that extends tens of thousands of kilometers into space, far beyond our atmosphere. Its primary role is to deflect the solar wind, a constant and ferocious stream of charged particles blasted from the sun. Without this shield, the solar wind would strip away our precious atmosphere, rendering the surface sterile and lifeless, much like the barren landscape of Mars. Yet, this vital shield is not static or fixed. The magnetic North Pole, the point on the Earth's surface where the magnetic field lines point vertically downwards, and where a compass needle would stubbornly try to stand on end, is a wanderer. When it was first formally located in 1831 by the explorer James Clark Ross, it was found in the bleak wilderness of the Canadian Arctic. Since then, and especially in recent decades, its journey has accelerated, moving northward across the Arctic Ocean at a remarkable pace of over 55 kilometers, or about 34 miles, per year, a tangible sign of the unpredictable fluid dynamics churning within the Earth's liquid outer core. Even more dramatic than this polar wandering is the phenomenon of geomagnetic reversal. Throughout our planet's long history, the magnetic poles have completely flipped, with north becoming south and south becoming north, on average, every few 100,000 years. Evidence for these ancient reversals is indelibly written into the rock of the ocean floor. As new crust forms at mid-ocean ridges, molten rock erupts and cools, and the iron, rich minerals within it align themselves with the prevailing magnetic field of the time. This process creates a symmetrical pattern of magnetic stripes on either side of the ridge, a geological barcode that records our planet's magnetic past. While these internal and external forces shape our world, the entire planet is on a colossal journey of its own. As we go about our lives, tethered by gravity to its surface, we are hurtling through the vacuum of space, orbiting the sun at an incredible speed. This velocity is approximately 107,000 kilometers per hour, which is about 67,000 miles per hour. We feel nothing of this cosmic motion, passengers on a planetary vessel making its ceaseless, high-speed voyage around its star. This grand orbital journey, a celestial circuit that our planet completes once every 365.24 days, defines the length of our year. That small fraction, just under a quarter of a day, might seem insignificant, but it accumulates. If we ignored it, our calendar would drift out of alignment with the seasons by a full day every 4 years. It was a problem that vexed calendar makers for millennia, from the ancient Egyptians to the Romans. The solution, which we still use today, is the leap year, a simple but elegant correction that adds an extra day to our calendar every 4th year, resynchronizing our measure of time with the planet's actual position in its orbit. But the changing of the seasons themselves is not governed by our proximity to the sun, a common misconception born from the experience of a warm summer and a cold winter. The true architect of our seasons is the planet's orientation in space. Earth does not sit upright as it spins and orbits. Rather, it leans, tilted on its axis by a constant 23.4 degrees. This axial tilt means that for half of the year, the northern hemisphere is angled more directly towards the sun, receiving more concentrated solar energy, which brings about its spring and summer. During this same period, the southern hemisphere is angled away, experiencing the more glancing, less intense rays that define its autumn and winter. The situation then reverses as the Earth continues its journey to the other side of the sun, bringing summer to the south and winter to the north. This simple, persistent lean is the engine of our planet's climatic rhythm, a celestial nod that gives us the cyclical beauty of the seasons. Nowhere are the consequences of this axial tilt more profound than at the poles, the planet's lonely and frozen extremities. The southernmost continent, Antarctica, is a realm of superlatives, a landmass almost entirely buried beneath a colossal sheet of ice. This ice is so vast and so deep that it holds an astonishing 70% of all the fresh water on Earth. It also accounts for 90% of all the planet's ice, a frozen reservoir of immense global significance. In some places, this ice sheet is more than 4 kilometers, or nearly 3 miles, thick, a weight so immense that it has pushed the underlying bedrock down by hundreds of meters. This continent of ice is also the site of the most extreme cold ever encountered on our planet's surface. At the Soviet research outpost of Vostok Station, located deep within the continent's interior and high on the polar plateau, scientists recorded the lowest natural temperature in history on a dark winter day in 1983. The air temperature plunged to a staggering negative 89.2 degrees Celsius, a chilling negative 128.6 degrees Fahrenheit. At such temperatures, the very air feels different, and a breath of it can cause the lungs to hemorrhage. It is a cold so absolute that it redefines the limits of life and the endurance of the human spirit. From this pole of absolute cold, we can travel in our minds to the planet's pole of extreme heat. In the stark, beautiful, and aptly named Death Valley in California, a part of the larger Mojave Desert, lies a place called Furnace Creek. Here, in the summer of 1913, the opposite world record was set. The air temperature soared to a blistering 56.7 degrees Celsius, or 134 degrees Fahrenheit, the highest reliably measured air temperature on Earth. This scorching heat is the result of the valley's unique geography. It is long, deep, and narrow, sinking to 86 meters, or 282 feet, below sea level. The high, steep mountains that flank the valley trap the hot air, which is heated further as it sinks and is compressed, creating a veritable oven. The extremes of our world are not limited to temperature alone. In South America, west of the Andes Mountains, lies the Atacama Desert, a coastal strip of land in Chile that holds the title of the driest non-polar desert on the planet. This extraordinary aridity is the product of a powerful 1-2 punch of geographic circumstance. The towering Andes Mountains to the east create a formidable barrier, blocking all moisture from the Amazon basin, a phenomenon known as a rain shadow. To the west, the cold Humboldt Current flows up from the Antarctic, chilling the air and preventing the formation of rain clouds. The result is a landscape so parched that some weather stations there have never recorded a single drop of rain. The soil is often compared to that of Mars, and the region is so alien and lifeless that scientists and space agencies frequently use it as a testing ground for rovers and instruments destined for the red planet. From the driest place on the surface, we now descend into the abyssal depths of the ocean to find another of Earth's great extremes. In the western Pacific lies the Mariana Trench, a crescent-shaped scar in the Earth's crust that plummets to the deepest point on the planet's surface. Its lowest point, the Challenger Deep, reaches a depth of nearly 11,000 meters, or almost 36,000 feet. To put this into perspective, if you were to place Mount Everest, the highest peak on land, into the Challenger Deep, its summit would still be submerged beneath more than 2 kilometers, or well over a mile, of water. The pressure here is crushing, over 1,000 times greater than at sea level, a force equivalent to having 50 jumbo jets stacked on top of you. Yet, even in this dark, cold, high-pressure world, life finds a way to exist. Our planet's topography is not only defined by its great depths, but also by its immense mountain ranges. However, the longest mountain range on Earth is not the Andes or the Himalayas. It is a feature almost entirely hidden from our view, a colossal chain of underwater volcanoes known as the Mid-Ocean Ridge. This ridge system is a continuous geological feature that snakes for 65,000 kilometers, or some 40,000 miles, around the globe, like the seam on a baseball. It is the place where the Earth's tectonic plates are pulling apart, allowing magma from the mantle to erupt and create new oceanic crust. This volcanic spine runs down the center of the Atlantic, curves around Africa, through the Indian Ocean, and across the Pacific. A testament to the dynamic, restless nature of our planet's geology. This underwater world forces us to reconsider our very definition of what makes a mountain tall. While Mount Everest holds the record for the highest altitude above sea level, the title of the tallest mountain on Earth, measured from its base to its summit, belongs to Mauna Kea, a dormant volcano on the island of Hawaii. While its peak stands at 4,207 meters, or 13,803 feet, above the Pacific, its true base lies nearly 6,000 meters, or about 20,000 feet, below the waves on the deep ocean floor. Its total height from base to peak is over 10,000 meters, or more than 33,000 feet, making it significantly taller than Everest. Finally, we turn from the grand scale of geological formations to the largest structure ever built by life itself. Off the northeastern coast of Australia lies the Great Barrier Reef, a living masterpiece so vast that it is visible from space. It is not a single, solid wall, but a breathtakingly complex mosaic of nearly 3,000 individual reefs and 900 islands, stretching for over 2,300 kilometers, or 1,400 miles. This colossal ecosystem was built over millennia by billions upon billions of tiny animals known as coral polyps, each secreting a limestone skeleton that over countless generations forms the intricate and massive structures we see today. The reef is a vibrant, teeming metropolis of marine life, one of the most biodiverse places on the entire planet, a living testament to the power of collective, unconscious creation on a geological timescale. In that same stark expanse of Death Valley, home to the world's highest recorded temperature, lies another more subtle mystery. On a dry lake bed known as racetrack playa, heavy stones, some weighing hundreds of kilograms or several hundred pounds, have been observed to move across the flat surface, leaving long, shallow trails etched into the cracked mud behind them. For decades, this phenomenon of the sailing stones baffled scientists, giving rise to all manner of speculation. The truth, finally documented in the early 21st century, is a delicate conspiracy of rare conditions. A light rain must fall, just enough to form a shallow pond, which then freezes overnight into a thin sheet of ice. As the morning sun warms the ice, it begins to break up into large, floating panels. Light winds, gliding across the vast, flat playa, then push these ice sheets, which, in turn, act as rafts, ferrying the embedded rocks on a slow, silent journey across the slick mud below. This interplay of wind and ice is a product of our planet's atmosphere, the gaseous envelope that not only enables such delicate phenomena, but shields and sustains all life. While it seems substantial to us, it is, from a planetary perspective, an incredibly thin and fragile veil. Its composition is dominated by two gases. About 78% is nitrogen, a relatively inert gas that provides bulk, and a crucial 1% is oxygen, the fuel for our own respiration and that of most complex life. The remaining 1% is a mix of argon, carbon dioxide, and trace amounts of other gases that have an outsized impact on our climate. This atmosphere is not a uniform blanket, but a structured, layered shield, with 5 distinct layers stacked on top of one another. We live and breathe in the lowest layer, the troposphere, which contains nearly all of the atmosphere's water vapor and is where our weather occurs. Above that lies the stratosphere, a calm, clear region where commercial jets cruise to avoid the turbulence of the troposphere. It is here, within the stratosphere, that a tenuous but critical concentration of molecules called ozone resides. This ozone layer is our planet's primary defense against the sun's most damaging rays, absorbing the most energetic and dangerous frequencies of ultraviolet radiation before they can reach the surface and harm living organisms. Journeying higher, we would pass through the mesosphere, the layer where most meteors, drawn by Earth's gravity, burn up in spectacular, fleeting streaks of light. Above that is the thermosphere, where the International Space Station orbits and where the beautiful auroras dance. And finally, the exosphere, the thinnest, outermost layer that gradually fades into the vacuum of space. But the ground beneath our feet, shielded by this complex atmosphere, is anything but tranquil. It is a fractured mosaic of tectonic plates, constantly grinding against one another, building mountains, and unleashing immense energy. The most powerful earthquake ever recorded by seismographs struck the coast of southern Chile on a May afternoon in the year 1960. Registering a magnitude of 9.5 on the moment magnitude scale, the Valdivia earthquake was an event of almost unimaginable power. The rupture zone was immense, stretching for nearly 1,000 kilometers, or over 600 miles, along the coast. The shaking lasted for more than 10 minutes, and the ground itself was seen to move in visible waves. The energy released was so vast that it caused the entire planet to vibrate, an oscillation that was measured for days afterwards. The quake also triggered a colossal tsunami that devastated the Chilean coastline and then raced across the entire Pacific Ocean, causing death and destruction as far away as Hawaii, Japan, and the Philippines. This same volcanic activity that drives the tectonic plates can manifest in stranger, more insidious ways. In the highlands of Cameroon, Africa, lie several deep volcanic lakes, including Lake Nio and Lake Monon. In 1986, Lake Nio became the site of a horrifying natural disaster. Without warning, the lake suddenly released a massive, invisible cloud of carbon dioxide gas that had been seeping from a magma chamber below the lake bed and dissolving into the deep, cold water for centuries. Being heavier than air, this cloud of gas silently rolled down the surrounding valleys, displacing the oxygen. The very air became a poison, suffocating over 1,700 people and thousands of livestock in their sleep. Despite these ever-present dangers, life has flourished on our planet with an almost defiant exuberance. The current scientific consensus estimates that our planet is home to roughly 8.7 million distinct species, a number so vast it is difficult to comprehend. And this is only an estimate. Millions more species, particularly insects, fungi, and deep-sea organisms, are believed to exist, still unknown to science. Among this staggering biodiversity, some organisms achieve scales of size and age that challenge our very definitions of an individual. The largest single living entity ever discovered is not a whale or a giant tree, but a fungus. Deep in the Malheur National Forest in Oregon, a single organism of the species Armillaria ostoyi, popularly known as the honey mushroom, spreads its filament-like network underground. It covers over 965 hectares, or nearly 2,400 acres, a silent, creeping colossus that is thousands of years old. From the largest, we turn to the oldest known individual, non-clonal organism. In the stark, wind-swept White Mountains of California, at an altitude of over 3,000 meters, or about 10,000 feet, grows a great basin bristlecone pine. Guarded in an undisclosed location for its protection, and given the name Methuselah, it is over 4,850 years old. This single tree was already a mature specimen when the pyramids of Giza were being built and has stood a silent witness through the rise and fall of countless human civilizations. This tree has stood rooted while the very continents have drifted beneath it. For our world map is not a permanent fixture. all the Earth's major landmasses were once fused together into a single, colossal supercontinent, known to geologists as Pangaea. This massive continent, which existed during the late Paleozoic and early Mesozoic eras, was surrounded by a single global ocean. Over the course of millions of years, the same tectonic forces that cause earthquakes and volcanoes today ripped Pangaea apart, setting the continents on their slow, inexorable drift towards the positions they occupy today. The vast, single ocean that once surrounded Pangaea has since been divided into the major ocean basins we know today. The largest and deepest of these is the Pacific Ocean, a body of water so immense that it covers about 1/3 of the entire surface of our planet. Its area is larger than all of the Earth's land masses combined, a truly staggering expanse of blue. It is a world of its own, containing the deepest trenches, the tallest underwater mountains, and the most remote islands on the globe. Its currents shape global weather patterns, and its depths hold mysteries we are only just beginning to unravel. Within these immense volumes of seawater, a hidden treasure exists, scattered in trace amounts. The oceans contain more than 20 million tons of dissolved gold. However, this vast fortune is so incredibly diluted, with concentrations in the range of parts per trillion, that extracting it is not economically feasible with current technology. To obtain a single gram of gold, you would need to process thousands of metric tons of seawater, a testament to the sheer scale of the ocean's chemistry. This immense marine realm is still largely a foreign territory to us. Despite our technological advancements and our innate curiosity, humans have explored less than 20% of the Earth's oceans. The vast majority of the underwater world, particularly the deep sea, remains unmapped, unobserved, and unexplored. We know more about the surface of the Moon and Mars than we do about the floor of our own planet's oceans, a humbling reminder of the challenges of exploring a realm of crushing pressure, total darkness, and extreme cold. Even our traditional concepts of geography, like the idea of a waterfall, are challenged by the ocean's hidden dynamics. The world's largest waterfall is not on land, but is a submerged feature in the Denmark Strait, the narrow passage of ocean between Greenland and Iceland. This underwater cataract, known as the Denmark Strait Cataract, is a place where cold, dense water from the Nordic seas meets the warmer, lighter water of the Erminger Sea. The denser water flows over a huge drop in the ocean floor, plunging over 3,500 meters, or about 11,500 feet, from the Greenland Sea into the North Atlantic. Its flow rate is colossal, estimated at over 5 million cubic meters per second, which is more than 2,000 times the flow of Niagara Falls. This silent, invisible cascade is a critical component of the global ocean circulation system, a powerful engine driving the deep currents that transport heat and nutrients around the planet. Back on land, another form of liquid power shapes the continents. The great river systems of the world act as the planet's arteries, carrying water, sediment, and life across vast distances. In South America, the Amazon River and its surrounding rainforest form one of the most vital ecosystems on Earth. The Amazon basin is so vast and so dense with life that it produces approximately 20% of the world's oxygen, a byproduct of the relentless photosynthesis occurring in its trillions of leaves. It is often referred to as the lungs of the planet, a title that underscores its critical role in maintaining the balance of our global atmosphere. This abundance of liquid water, whether in oceans, ice caps, or rivers, is the single most important feature of our planet. Earth is the only known planet in the universe to have stable, liquid water on its surface. This simple molecule is the universal solvent, the medium in which the complex chemistry of life as we know it takes place. Its presence has allowed life to emerge, to thrive, and to diversify into the millions of species that inhabit our world today. And the story of life on Earth is an ancient one. The first stirrings of biology, the earliest, simplest forms of life, appeared in the primordial oceans approximately 3.8 billion years ago. These were microscopic, single-celled organisms, likely clustered around hydrothermal vents on the deep ocean floor, drawing energy not from the sun, but from the chemical reactions fueled by the planet's internal heat. For billions of years, these simple microbes were the sole inhabitants of the planet, slowly and profoundly changing its chemistry. A pivotal moment in this planetary transformation was the Great Oxidation Event, which occurred about 2.4 billion years ago. This was not a sudden catastrophe, but a gradual, global change brought about by the evolution of a new type of bacteria, cyanobacteria. These tiny organisms developed a revolutionary new metabolic process, photosynthesis, which allowed them to harness the energy of sunlight to create food. As a byproduct of this process, they released oxygen, a highly reactive and, at the time, toxic gas. Over hundreds of millions of years, this waste product accumulated, first in the oceans, where it caused iron to rust and fall to the seabed, and then in the atmosphere. This dramatic rise in atmospheric oxygen was a poison to most of the anaerobic life that existed at the time, causing the planet's first major mass extinction. But it also paved the way for the evolution of new, more complex life forms that could harness the power of oxygen through respiration, the very process that sustains us today. The history of life on Earth has been punctuated by several of these catastrophic episodes. Our planet has experienced 5 major mass extinctions, periods of intense environmental change where a significant percentage of all living species disappeared in a relatively short geological time frame. The most famous of these is the Cretaceous-Paleogene extinction event, which occurred 66 million years ago and marked the end of the age of dinosaurs. But it was not the largest. That grim title belongs to the Permian-Triassic extinction, often called the Great Dying, which happened 252 million years ago and wiped out an estimated 96% of all marine species and 70% of terrestrial vertebrate species. These events, devastating as they were, also created opportunities for the survivors to diversify and evolve, shaping the course of life in profound ways. The sheer number of species that have come and gone is staggering. It is estimated that over 99% of all species that have ever lived on Earth are now extinct. Life on our planet is a story of constant creation and constant loss, a dynamic and often brutal process of adaptation and change, with every living thing today representing a branch on a vast and ancient family tree, a lineage that has somehow navigated these profound challenges through deep time. Our planet's surface is in a constant state of renewal, a quiet, continuous process of accumulation. Every single day, the Earth is showered with a fine rain of material from space, a gentle but persistent bombardment of micrometeorites and cosmic dust. Scientists estimate that roughly 100 tons of this extraterrestrial material falls to the surface daily. Most of these particles are minuscule, no larger than a grain of sand, and they are the remnants of comets and asteroids that have been orbiting the Sun for billions of years. As the Earth plows through this cosmic debris field on its journey around the Sun, these tiny particles enter our atmosphere at incredible speeds and burn up. But the resulting dust drifts slowly down, settling invisibly on rooftops, in oceans, and on polar ice sheets. This constant influx from the cosmos has been happening since the planet's formation, a subtle but unending connection between our world and the wider solar system. In stark contrast to this gentle cosmic rain, our planet's atmosphere can unleash events of focused and terrifying energy. A single bolt of lightning, a fleeting discharge of atmospheric electricity that lasts for only a fraction of a second, can heat the air in its path to a temperature of 30,000 degrees Celsius, or about 54,000 degrees Fahrenheit. This is a temperature 5 times hotter than the surface of the Sun. This extreme heating causes the air to expand explosively, creating a shock wave that we hear as thunder. Lightning is a raw and powerful demonstration of the electrical forces at play within our weather systems, a dramatic release of the energy that builds up within turbulent storm clouds. Beyond the drama of the skies, the Earth holds landscapes of profound stillness and beauty that harbor their own deep mysteries. In the forests of our world, a quiet and profound truth is hidden in plain sight. There are more trees on Earth than there are stars in our home galaxy, the Milky Way. Current estimates suggest that our planet is home to over 3 trillion trees, a staggering number that forms the backbone of countless ecosystems. In contrast, astronomers estimate that the Milky Way galaxy contains somewhere between 100 and 400 billion stars. This simple comparison highlights the incredible richness and density of life on our own world, a biological abundance that can, in some ways, outnumber the stars in our galactic neighborhood. The history of our planet is not just written in the stars or in the living world, but in the very rocks beneath our feet. The oldest known rocks on Earth were discovered in northern Quebec, Canada, on the shores of Hudson Bay. These ancient formations, part of what is known as the Nouveau-Jitup Greenstone Belt, have been dated to be as old as 4.28 billion years old. These rocks are not much younger than the planet itself, and they provide a rare and precious window into the Hadean Eon, the fiery and tumultuous period of Earth's earliest history. They are a tangible link to a time when the planet was still cooling from its molten birth, when the first continents were beginning to form, and when the stage was being set for the emergence of life. Deep within the planet's interior, far below these ancient rocks, lies the Earth's core. This central region of our planet is a world of extreme temperature and pressure. Scientists have calculated that the temperature at the center of the Earth is approximately 6,000 degrees Celsius, or about 10,800 degrees Fahrenheit, a temperature as hot as the surface of the sun. This intense heat is the remnant of the planet's violent formation and is also sustained by the slow decay of radioactive elements within the core itself. This internal furnace is the engine that drives many of the planet's most important geological processes, from the movement of tectonic plates to the generation of our protective magnetic field. This core is not a single uniform entity, but is composed of two distinct layers with radically different properties. The inner core, a sphere of mostly iron and nickel, about the size of the moon, is under such immense pressure that, despite the incredible heat, it is forced into a solid state. Surrounding this solid heart is the outer core, a thick layer of molten iron and nickel. It is the constant, churning motion of this liquid metal, driven by the planet's rotation and the heat flowing from the inner core, that acts as a giant dynamo, generating the Earth's magnetic field. This dynamic, two-part structure is a key feature of our planet's deep interior, a hidden world whose behavior has profound consequences for the surface. The planet's daily rotation, the very spin that drives the dynamo in the core, also has a more subtle effect on the movements of fluids on its surface. This is known as the Coriolis effect, an inertial force that deflects moving objects, including air and water, to the right in the northern hemisphere and to the left in the southern hemisphere. It is this effect that dictates the rotation of large-scale weather systems, causing hurricanes and typhoons to spin counterclockwise in the north and clockwise in the south. It also influences the direction of major ocean currents, helping to create the complex patterns of circulation that distribute heat around the globe. The solid surface of our planet, the very ground we stand on, is in a state of perpetual, albeit incredibly slow, transformation. The Earth's rock cycle is a fundamental concept in geology that describes how the three main types of rock, igneous, sedimentary, and metamorphic, are created, and how they are transformed from one type to another over vast stretches of time. Igneous rocks are formed from the cooling and solidification of molten rock, or magma. When these rocks are exposed on the surface, they are weathered and eroded into smaller particles, which are then transported by wind and water and deposited in layers. Over time, these layers are compacted and cemented together to form sedimentary rocks. If these rocks are then subjected to intense heat and pressure deep within the Earth's crust, they are transformed into metamorphic rocks. And if the heat is great enough, they will melt back into magma, beginning the cycle anew. This endless process of creation, destruction, and transformation is a cornerstone of our planet's geology. Our planet's history may also hold a story of a lost celestial companion. Some scientific models and evidence from lunar rock samples suggest that in the distant past, the Earth may have had two moons. The theory posits that a second, smaller moon was also formed from the same giant impact that created our current moon. This smaller moon would have shared an orbit with its larger sibling for tens of millions of years before eventually succumbing to its gravitational pull and slowly, gently colliding with it. This slow-motion impact would have plastered the smaller moon's material onto one side of the larger moon, which could explain the significant and long-standing mystery of why the moon's far side has a much thicker crust and a different composition than the near side. Our remaining moon, the familiar silver disk in our night sky, is not a permanent fixture in its current orbit. It is slowly but surely drifting away from the Earth at a rate of about 3.8 centimeters, or 1.5 inches, per year. This gradual retreat is caused by the same tidal forces that are slowing the Earth's rotation. The Earth's gravitational pull creates a tidal bulge on the moon, and the moon's pull creates the ocean tides on Earth. Because the Earth rotates faster than the moon orbits it, the Earth's tidal bulge is always slightly ahead of the moon, pulling it forward in its orbit. This constant forward tug transfers rotational energy from the Earth to the moon, causing the moon to accelerate and move into a higher orbit, farther away. This process has been happening since the moon's formation, and billions of years ago, the moon would have appeared much larger and more imposing in our sky. Our planet's physical properties set it apart from its neighbors in the solar system in several fundamental ways. One of the most significant is its density. Earth is the densest planet in our solar system, with an average density of about 5.5 grams per cubic centimeter. This high density is a direct result of its composition, particularly the large, dense iron-nickel core at its center. The rocky planets, Mercury, Venus, Earth, and Mars, are all denser than the gas giants, Jupiter, Saturn, Uranus, and Neptune, which are composed mostly of lighter elements like hydrogen and helium. But among the rocky worlds, Earth holds the top spot, a consequence of the gravitational compression of its materials and the sheer size of its metallic heart. This dense, solid planet is in a constant gravitational embrace with its large moon, a relationship that manifests most dramatically in the rhythm of our ocean tides. The moon's gravitational pull creates a bulge in the Earth's oceans on the side of the planet closest to it, and a corresponding bulge on the opposite side. As the Earth rotates beneath these bulges, coastal areas experience the cyclical rise and fall of sea level that we call the tides. While all coastlines experience this phenomenon, certain geographic locations amplify it to an extraordinary degree. The highest tides in the world are found in the Bay of Fundy, a long, funnel-shaped bay on the Atlantic coast of North America, between the Canadian provinces of New Brunswick and Nova Scotia. Here, the shape and resonance of the bay are perfectly tuned to the Atlantic's tidal rhythm, causing the water to slosh back and forth in a way that magnifies the tidal effect. The difference between high and low tide in the Bay of Fundy can be more than 16 meters, or over 53 feet, a vertical change equivalent to a 5-story building. This colossal movement of water shapes the coastline, creates unique ecosystems, and is a powerful testament to the lunar forces acting upon our world. Our planet's atmosphere, the same gaseous envelope that creates our weather and shields us from harmful radiation, also provides a crucial defense against another celestial threat: meteoroids. Every day, countless small particles of rock and ice from space, ranging in size from dust grains to small boulders, enter the Earth's atmosphere. Traveling at hypersonic speeds, these objects encounter immense friction and compression as they plow into the air. This process generates intense heat, causing most of them to vaporize and burn up long before they can reach the ground, creating the fleeting streaks of light we call meteors or shooting stars. This atmospheric shield is incredibly effective, protecting the surface from what would otherwise be a constant and destructive rain of high-velocity projectiles. Without it, the Earth's surface would be heavily cratered, much like the Moon's. The concept of a desert often conjures images of vast, sun-scorched landscapes of sand and rock. While this is true for hot deserts, the technical definition of a desert is a region that receives very little precipitation. By this measure, the largest desert in the world is not a hot one, but a cold one. The Antarctic polar desert covers the entire continent of Antarctica, an area of some 14 million square kilometers, or 5.5 million square miles. The air there is so cold that it holds very little moisture, and the average annual precipitation over much of the continent is less than 200 millimeters, or about 8 inches, most of it falling as snow. The interior of the continent is even drier, making it the coldest, driest, and highest continent on Earth. In contrast, the largest hot desert in the world is the Sahara, which stretches across the northern part of Africa. Covering an area of over 9 million square kilometers, or 3.5 million square miles. It is a vast realm of sand seas, rocky plateaus, and barren gravel plains where rainfall is scarce and temperatures can soar. The very ground beneath these deserts, and indeed beneath the entire surface of the planet, is not a single solid shell. The Earth's crust is broken into a number of large, rigid sections called tectonic plates. These plates, which range in size from minor ones to the colossal Pacific Plate, are constantly in motion, floating on the semi-molten layer of the upper mantle below, a region known as the asthenosphere. Their movement is incredibly slow, typically only a few centimeters per year, about the same speed at which our fingernails grow. But over the vast time scale of geology, this slow, steady movement is responsible for the most dramatic features of our planet's surface. The interactions at the boundaries where these plates meet are the primary drivers of the Earth's geological activity. Where plates pull apart, as at the mid-ocean ridge, new crust is formed. Where they collide, one plate is often forced to slide beneath the other in a process called subduction, which can create deep ocean trenches and chains of volcanoes. Where plates slide past each other horizontally, they create massive fault lines. It is the movement of these plates, the grinding, sticking, and sudden slipping at their boundaries, that causes the vast majority of the world's earthquakes and volcanic eruptions. This has led to the identification of a region of intense geological activity known as the Ring of Fire. This horseshoe-shaped zone stretches for 40,000 kilometers, or 25,000 miles, around the basin of the Pacific Ocean, tracing the boundaries of the massive Pacific Plate with several other smaller plates. This region is home to over 75% of the world's active and dormant volcanoes, and is the site of about 90% of the world's earthquakes, including the most powerful ones ever recorded. It is a vivid and dynamic illustration of the immense forces at work just beneath the surface of our seemingly solid planet. This volcanic activity is a constant feature of our world. At any given time, there are about 1,500 potentially active volcanoes on Earth, not including the continuous chain of volcanoes on the ocean floor. Of these, around 50 to 70 erupt each year, spewing ash, gas, and lava, and reshaping the surrounding landscape. This volcanism is a vital planetary process, a way for the Earth to vent its internal heat, and a key part of the rock cycle that creates new land. While many volcanoes are impressive in size, one stands out as the largest active volcano on the planet. Mauna Loa, one of the 5 volcanoes that form the island of Hawaii, is a true giant. While it is not as tall as its neighbor, Mauna Kea, when measured from its base on the seafloor, Mauna Loa is far more massive. Its volume is estimated to be around 75,000 cubic kilometers, or 18,000 cubic miles, making it the most voluminous volcano on Earth. Its gentle, shield-like slopes are the result of countless flows of very fluid lava over hundreds of thousands of years, a slow and steady process of construction that has built a mountain of immense skill and power. Beyond the grand, violent phenomena of volcanoes and earthquakes, our planet produces a much subtler, more mysterious signal. Scientists have detected a faint, persistent, low-frequency vibration that seems to be present everywhere on the globe. Known to seismologists as the Earth's hum, this microseismic signal is a continuous tremor that is too faint for humans to feel, but it is constantly being recorded by sensitive seismographs. For a long time, its origin was a puzzle. Initial theories suggested it was caused by the collective noise of human activity or the crashing of ocean waves. However, recent research suggests that a significant portion of this hum is generated by the rhythmic, gentle sloshing of ocean waves over the vast continental shelves. As long-period ocean waves move across the seafloor, the pressure variations on the bottom are thought to generate seismic waves that propagate throughout the solid Earth, causing the entire planet to resonate with a faint, inaudible sound. From this global vibration, we can turn our attention to the great land masses of our world. The definition of a continent versus an island is a matter of geological and historical convention. But by the standard geographical definition, the world's largest island is Greenland. Located between the Arctic and Atlantic Oceans, this massive landmass covers an area of over 2 million square kilometers, or more than 100,000 square miles. Despite its name, which was given by the Norse explorer Eric the Red in an attempt to attract settlers, about 80% of Greenland is covered by a vast ice sheet, second in size only to the one in Antarctica. This ice, in some places up to 3 kilometers, or nearly 2 miles, thick, conceals a mountainous, barren rock landscape beneath it. The land beneath us, whether it is part of a vast continent or a remote island, is not static. The continents themselves are in a state of constant, slow-motion drift, a process that is continuously reshaping the world map over geological time. At the boundaries of these continents, and in geologically unique regions, we find some of the planet's most extreme points of elevation. One of the most remarkable of these is the shoreline of the Dead Sea, a salt lake bordered by Jordan to the east and Israel and the West Bank to the west. The surface and shores of the Dead Sea are more than 430 meters, or over 1,400 feet, below sea level, making it the lowest point on the Earth's land surface. This extreme low elevation is a result of its location in the Dead Sea Rift, a tectonic fault zone where the Arabian Plate is pulling away from the African Plate. The lake itself is famous for its extreme hypersalinity, which makes the water more dense that people can float in it effortlessly. The climate of our planet, the long-term pattern of temperature, precipitation, and wind, has not always been as it is today. The Earth's history is marked by significant and sometimes dramatic climate shifts, including several major ice ages. These were periods when the global climate was much colder, and vast sheets of ice, similar to those in Greenland and Antarctica today, covered large portions of North America, Europe, and Asia. We are currently in a warmer interglacial period within a larger ice age that began over 2.5 million years ago. These long-term climatic cycles are not random. They are driven by a combination of factors, including a set of predictable, repeating changes in the Earth's orbit around the Sun. These orbital variations are known as the Milankovitch cycles, named after the Serbian astrophysicist Milutin Milankovic, who developed the theory in the early 20th century. He identified 3 primary ways in which the Earth's orbit changes over long periods. First, the shape of the Earth's orbit, its eccentricity, varies from being nearly circular to more elliptical over a cycle of about 100,000 years. Second, the tilt of the Earth's axis, its obliquity, changes between about 22 and 24.5 degrees over a period of about 41,000 years. And third, the Earth's axis wobbles like a spinning top, a phenomenon called precession, which has a cycle of about 26,000 years. These cycles, unfolding over immense timescales, alter the amount and distribution of solar radiation reaching the Earth, and they are now understood to be the primary pacemaker of the ice ages. In addition to the planet's 2 great polar ice caps, there is another region that holds such a vast amount of ice that it is often referred to as the third pole. This is the Tibetan Plateau, a vast, elevated plateau in Central Asia that is the highest and largest in the world. The plateau and the surrounding mountain ranges, including the Himalayas, Hindu Kush, and Tian Shan, contain the largest concentration of glaciers and ice fields outside of the Arctic and Antarctic regions. These glaciers act as a critical water tower for Asia, feeding the continent's major river systems, including the Indus, Ganges, Brahmaputra, Yangtze, and Yellow rivers. The seasonal meltwater from these glaciers provides a vital source of fresh water for billions of people downstream, making this third pole a crucial component of the regional and global climate system. The fresh water stored in these glaciers and found in rivers and lakes around the world represents only a tiny fraction of the planet's total water. While Earth is often called the water planet, about 97% of its water is salt water in the oceans. Of the remaining 3% that is fresh water, The vast majority, nearly 70%, is locked up as ice in glaciers and ice caps. Most of the rest is stored underground as groundwater. This means that the easily accessible fresh water in rivers and lakes, the water that sustains most terrestrial life and human societies, makes up less than 1% of all the water on the planet, highlighting it as an incredibly precious and limited resource. Within the planet's diverse ecosystems, from the dark depths of the ocean to the forest floor, a magical phenomenon occurs: bioluminescence. This is the ability of living organisms to produce their own light through a chemical reaction. It is a form of cold light, meaning that very little heat is generated during the process. Bioluminescence has evolved independently many times and is used by a wide variety of creatures, including fireflies, fungi, bacteria, and a vast array of marine animals like jellyfish, squid, and deep-sea fish. They use this ability for many purposes: to attract mates, to lure prey, to communicate, and to defend themselves by startling predators. It is a beautiful and ethereal example of the diverse ways in which life has adapted to thrive on our world. Another spectacular display of light, this one originating from the sun, is the aurora. The aurora borealis, or northern lights, and its southern counterpart, the aurora australis, are natural light displays that shimmer and dance across the sky in the high latitude regions. They are created when energetic, charged particles from the sun, carried by the solar wind, are channeled by the Earth's magnetic field towards the poles. As these particles collide with atoms and molecules of gas in the upper atmosphere, primarily oxygen and nitrogen, they excite those atoms, causing them to emit light of different colors. Green and red auroras are typically produced by oxygen, while blue and purple hues are created by nitrogen. The color of our sky itself is a result of a phenomenon called Rayleigh scattering. As sunlight, which is composed of all the colors of the spectrum, enters the Earth's atmosphere, it collides with the tiny gas molecules that make up the air. The shorter, bluer wavelengths of light are scattered more effectively in all directions by these molecules than the longer, redder wavelengths. When we look up at the sky on a clear day, what we are seeing is this scattered blue light coming at us from all directions, which is why the sky appears blue. As the sun gets lower on the horizon at sunrise and sunset, its light has to pass through more of the atmosphere to reach our eyes. This means that most of the blue light is scattered away, leaving the longer, redder wavelengths to continue on to our eyes, creating the brilliant orange and red colors of sunrise and sunset. This simple process of light scattering is responsible for one of the most fundamental and beautiful aspects of our planet's appearance. The Earth's early atmosphere, the one in which the first life emerged, would have been completely alien and toxic to us. It was a dense, hazy mixture composed primarily of gases released by volcanic activity, likely a concoction of water vapor, carbon dioxide, nitrogen, and significant amounts of methane and ammonia. Crucially, it was almost completely devoid of free oxygen. This reducing atmosphere, rich in hydrogen-containing compounds, is believed by many scientists to have been the perfect chemical soup for the origin of life, a place where complex organic molecules could form and persist without being destroyed by the corrosive effects of oxygen. It was only after the evolution of photosynthetic organisms over 1.5 billion years later that our atmosphere began its slow and dramatic transformation into the oxygen-rich air we breathe today. The transition of life from the oceans to the land was one of the most pivotal moments in the history of our planet. For billions of years, life had been confined to the water. The land was a barren, sterile wilderness. The first organisms to make the move from water to land were not animals, but plants. The earliest fossil evidence for land plants dates back to about 470 million years ago, during the Ordovician period. These early pioneers were likely related to modern bryophytes, such as mosses and liverworts. They would have lacked true roots, stems, and leaves, and would have hugged the ground in damp, marshy areas close to the water's edge. This colonization of the land by plants was a revolutionary event. They began to create soils, alter the composition of the atmosphere on a massive scale, and create new habitats that would eventually be colonized by the first land animals, such as insects and amphibians. Our planet possesses another feature that appears to be unique in our solar system, and may be one of the key reasons why complex life has been able to thrive here: plate tectonics. As we have seen, the Earth's outer shell is broken into a series of rigid plates that are in constant, slow motion. This process of plate tectonics is the driving force behind many of our planet's most dramatic geological features, including mountains, volcanoes, and earthquakes. But it does much more than that. Plate tectonics acts as a kind of planetary thermostat and life support system. The subduction of oceanic plates and the associated volcanism help to recycle chemicals and minerals that are essential for life, such as carbon and phosphorus, from the Earth's interior back to the surface. This recycling prevents these vital nutrients from being permanently locked away, ensuring a continuous supply for living organisms. The process also plays a crucial role in regulating the Earth's long-term climate by controlling the amount of carbon dioxide in the atmosphere. The constant creation and destruction of crust is a dynamic process that has kept our planet geologically and biologically active for billions of years. The fundamental rhythm of our lives, the cycle of days and night, is a direct consequence of the Earth's rotation on its axis. The planet completes one full spin approximately every 24 hours, which is what defines the length of our day. This rotation is what causes the sun to appear to rise in the east and set in the west. The speed of this rotation is fastest at the equator, where a point on the surface is moving at about 1,670 kilometers per hour, or just over 1,000 miles per hour. As you move towards the poles, this speed decreases until at the poles themselves, the speed is effectively zero. This daily spin is a deep and ancient feature of our planet, a motion that has governed the behavior and evolution of life since its very beginning. The idea that the Earth is a sphere, a concept that we take for granted today, was a profound intellectual leap in human history. It was first proposed by ancient Greek philosophers in the 6th century BC, most notably by Pythagoras and his school of thought. Their reasoning was based not on direct observation, but on philosophical and aesthetic grounds. They believed that the sphere was the most perfect and harmonious of all geometric shapes, and therefore the Earth must be a sphere. A couple of centuries later, Aristotle provided the first solid observational evidence for a spherical Earth. He noted that during a lunar eclipse, the shadow that the Earth casts on the moon is always circular, regardless of where the Earth is in its rotation. He also observed that as one travels north or south, new stars become visible above the horizon, while others disappear, a phenomenon that would not occur on a flat Earth. This understanding of our planet's true shape was a cornerstone of the scientific revolution. The ultimate proof of this spherical shape and a demonstration of the sheer scale of our world came from the first circumnavigation of the globe. This epic and perilous voyage was initiated by the Portuguese explorer Ferdinand Magellan, who set sail from Spain in 1519 with a fleet of 5 ships. Their goal was to find a westward route to the Spice Islands of Indonesia. The expedition was an ordeal of unimaginable hardship. They faced storms, starvation, disease, and mutiny. Magellan himself was killed in the Philippines. But one of his ship, the Victoria, under the command of the Basque navigator Juan Sebastian Elcano, managed to complete the journey, returning to Spain in 1522. Of the original crew of over 270 men, only 18 survived. This heroic and tragic voyage was the first to physically prove that the Earth is a sphere and that all its oceans are connected. The story of life on our planet is preserved in the fossil record, a vast and incomplete library of ancient organisms preserved in rock. The oldest of these fossils are of microorganisms, the simplest forms of life. In Western Australia, in a region of ancient rock known as the Pilbara Craton, scientists have discovered fossilized structures called stromatolites that are about 3.5 billion years old. These stromatolites are layered, dome-shaped structures that were built by colonies of single-celled cyanobacteria in shallow, sunlit water. The bacteria would form mats on the seafloor, trapping sediment and precipitating minerals, and would grow upwards towards the light, creating the distinctive layered patterns. These ancient fossils are a testament to the incredible antiquity of life on Earth and provide a direct link to the planet's earliest inhabitants. The changing seasons, the cyclical progression from spring to summer to autumn to winter, are one of the most profound and influential rhythms of our planet. A common misconception is that the seasons are caused by the Earth's changing distance from the Sun in its elliptical orbit. While our distance from the Sun does vary slightly throughout the year, this is not the primary cause of the seasons. The true reason, as we have touched upon, is the 23.4-degree tilt of the Earth's axis of rotation relative to its orbital plane. It is this axial tilt that causes the amount of direct sunlight reaching different parts of the globe to change over the course of the year, leading to the familiar seasonal cycle. Our planet's vast oceans are not just a reservoir of water. They are the primary regulator of the Earth's climate. Water has a very high heat capacity, meaning it can absorb and store large amounts of heat without its own temperature increasing dramatically. The oceans act as a massive global heat sink, absorbing a huge amount of solar energy, especially in the tropical regions. This heat is then transported around the globe by a system of powerful ocean currents, a process often referred to as the global ocean conveyor belt. This circulation of heat helps to moderate the planet's climate, preventing the equatorial regions from becoming excessively hot and the polar regions from becoming excessively cold regions from becoming excessively cold. The oceans and the atmosphere are in a constant, dynamic dance, exchanging heat, water, and gases, a partnership that creates the complex and ever-changing climate system of our world. Our planet is indeed a water world, a characteristic that makes it shimmer like a blue marble when viewed from the desolation of space. The sheer dominance of the oceans on our planet's surface is a feature that cannot be overstated. With the vast majority of its surface hidden beneath the waves, the true geography of our world is not one of continents, but of a single, interconnected global ocean, dotted with large islands of land. This marine realm is the engine of our climate, the cradle of life, and a world of such immense scale and depth that it remains the last great frontier of exploration on our own planet. The deep ocean floor is a landscape of towering mountain ranges, vast plains, and chasms far deeper than any canyon on land. Its existence shapes everything from our weather patterns to the very composition of the air we breathe. Despite its apparent stability, the Earth's atmosphere is not a closed system. It is in a constant, albeit very slow, process of leaking into space. High in the exosphere, the outermost, most tenuous layer of our atmosphere, atoms of light gases, primarily hydrogen and helium, can be accelerated by the solar wind and collisions with other particles to speeds that exceed the Earth's escape velocity. This process, known as atmospheric escape, causes our planet to lose a small but steady stream of its atmospheric gases to the vacuum of space at a rate of about 90 tons per day. While this sounds like a lot, the Earth's atmosphere is so massive that this loss is negligible over human timescales. But over the course of the planet's multi-billion-year history, it has had a significant impact on the atmosphere's overall composition. The Earth's magnetic field, the invisible shield generated by the molten iron in our planet's core, provides us with more than just protection from the solar wind. It is also the reason we can use compasses for navigation. A compass is, at its heart, a small, lightweight magnet that is free to rotate. The Earth's magnetic field exerts a torque on this magnet, causing it to align itself with the local magnetic field lines. The north pole of the compass magnet is attracted to the Earth's magnetic south pole, which is, somewhat confusingly, located near the geographic North Pole. For centuries, this simple, reliable tool has allowed sailors, explorers, and travelers to determine direction and navigate their way across the globe. It is a direct, tangible connection to the powerful and dynamic forces at work deep within our planet. The one constant about our world is that it is in a perpetual state of change. The planet is a dynamic and ever-evolving system, with its continents, oceans, and atmosphere locked in a constant state of flux. Continents drift, mountains rise and erode, oceans open and close, ice sheets advance and retreat, and the climate changes over a wide range of timescales. This ceaseless activity is a hallmark of a living, breathing planet. It is driven by the heat escaping from its interior and the energy pouring in from the sun. This dynamic nature is what makes the Earth such a complex, fascinating, and, at times, unpredictable place to live. One of the most profound ideas in all of science is the concept of a universal common ancestor. The theory of evolution, first articulated by Charles Darwin in the mid-19th century, proposes that all life on Earth is related and has descended from a single, common ancestral population of organisms that lived billions of years ago. This idea is supported by a mountain of evidence from genetics, comparative anatomy, and the fossil record. The fact that all known life forms use the same basic genetic code based on DNA is a powerful piece of evidence for this shared ancestry. It implies that every living thing on our planet, from the smallest bacterium to the largest blue whale, is a distant cousin, a twig on a single, vast, and ancient family tree of life. The process that powers this vast web of life is, for the most part, photosynthesis. This is the remarkable biochemical process used by plants, algae, and some bacteria to convert light energy from the sun into chemical energy in the form of glucose, a type of sugar. The overall equation for photosynthesis is that carbon dioxide and water, in the presence of sunlight, are converted into glucose and oxygen. This process is the foundation of nearly every ecosystem on Earth. It is the primary way in which energy from the sun enters the biosphere. The glucose it produces provides the fuel for the plant's own growth and metabolism, and it is the ultimate source of energy for all the animals that eat plants, and the animals that eat those animals. The oxygen it releases as a waste product is what transformed our atmosphere and made complex animal life possible. The incredible variety of life on Earth, the millions of different species that inhabit every conceivable niche on the planet, is what we call biodiversity. This biological diversity is not just a collection of interesting curiosities. It is essential for maintaining healthy, functioning ecosystems. A high level of biodiversity makes ecosystems more resilient to disturbances, such as climate change, disease, or pollution. Different species perform different roles in an ecosystem, and having a wide variety of species ensures that these roles, such as pollination, nutrient cycling, and decomposition, are carried out effectively. The intricate web of relationships between different species creates a stable and productive system that provides the essential resources, or ecosystem services, that human life depends on, including clean air, clean water, and fertile soil. The planet's ecosystems are not isolated, independent units. They are deeply and intricately interconnected. Changes in one ecosystem can have cascading and often unpredictable effects on others, even those that are geographically distant. For example, the health of the Amazon rainforest can influence rainfall patterns as far away as the central United States. The dust that blows from the Sahara Desert can provide essential nutrients to the rainforests of the Amazon and the marine ecosystems of the Atlantic Ocean. This interconnectedness means that our planet functions as a single, integrated system, a complex network of physical, chemical, and biological processes that are all linked. The revolutionary idea of continental drift, the theory that the Earth's continents have moved over geological time, was first proposed in a comprehensive way by a German meteorologist and geophysicist named Alfred Wegener in the early 20th century. Wegener was not the first to notice the remarkable jigsaw-like fit of the continents, particularly South America and Africa, but he was the first to gather a wide range of evidence to support the idea that they were once joined together. He pointed to the distribution of similar fossils, rock types, and ancient climate indicators on continents that are now widely separated. At the time, his theory was largely dismissed by the established geological community because he could not propose a plausible mechanism to explain how the continents could move. It was only in the 1960s, with the discovery of seafloor spreading and the development of the theory of plate tectonics, that Wegener's radical idea was finally vindicated, and he is now recognized as one of the great pioneers of Earth science. The Earth's interior is a layered world. Beneath the thin crust lies the mantle, a vast layer of silicate rock that extends down about 2,900 kilometers, or 1,800 miles, to the edge of the core. The mantle makes up about 84% of the Earth's volume. Although it is mostly solid rock, over the long timescales of geology, the mantle behaves like a very thick, viscous fluid, a property known as plasticity. It is the slow, convective churning of this semi-molten rock, driven by the heat from the core, that is the ultimate engine behind the movement of the tectonic plates on the surface. Our most detailed knowledge of the Earth's deep interior comes not from direct observation, but from studying the behavior of seismic waves generated by earthquakes. The science of seismology has allowed us to effectively CAT scan the planet. When an earthquake occurs, it sends out vibrations, or seismic waves, that travel through the Earth. There are different types of seismic waves, and they travel at different speeds and are reflected and refracted as they pass through materials of different densities and states. By analyzing the patterns of these waves as they are recorded by seismographs stationed all around the globe, scientists have been able to map out the major layers of the Earth's interior: the crust, mantle, outer core, and inner core, and to infer their composition and physical properties. It is this indirect, wave-based imaging that has given us our clearest picture of the hidden world that lies deep beneath our feet. The constant, predictable spin of the Earth on its axis is what creates the fundamental cycle of day and night. This rotation has a profound influence on all life on Earth, leading to the evolution of circadian rhythms, the internal biological clocks that govern the daily cycles of sleep, wakefulness, and metabolism in virtually all living organisms. This daily rhythm of light and dark, of activity and rest, is one of the most basic and universal experiences of life on our planet. The Earth's annual journey around the Sun is not a perfect circle, but a slightly flattened circle known as an ellipse. This means that our planet's distance from the Sun varies throughout the year. At its closest point, called perihelion, which occurs in early January, the Earth is about 147 million kilometers, or 91 million miles, from the Sun. At its farthest point, aphelion, in early July, it is about 152 million kilometers, or 94.5 million miles, away. While this variation in distance might seem significant, its effect on our seasons is minimal compared to the influence of our planet's axial tilt. Light travels through the vacuum of space at the ultimate cosmic speed limit, approximately 300,000 kilometers per second, or about 186,000 miles per second. The Sun is, on average, about 150 million kilometers, or 93 million miles, away from the Earth. A simple calculation reveals that it takes the light from the Sun about 8 minutes and 20 seconds to travel across this vast distance. This means that when we look at the Sun in the sky, we are not seeing it as it is in that instant, but as it was over 8 minutes ago. Every sunrise we witness is an event that has already happened, a delayed broadcast from our nearest star, a constant reminder of the immense scales of distance that define our place in the solar system. The Earth's atmosphere, the life-giving ocean of air in which we live, does not have a distinct, solid boundary where it ends and space begins. Instead, it gradually thins out with increasing altitude, becoming more and more tenuous until it eventually merges with the near vacuum of interplanetary space. For practical purposes, an arbitrary boundary has been established by the international community to define where aeronautics ends and astronautics begins. This is known as the Kármán line, located at an altitude of 100 kilometers, or about 62 miles above sea level. This line is a conceptual and legal demarcation. But physically, the outermost wisps of our atmosphere extend much farther into a region called the geocorona, which can reach hundreds of thousands of kilometers into space, well beyond the orbit of the Moon. As our planet spins on its axis, different parts of the globe experience day and night. To manage timekeeping on a global scale, an imaginary line was established on the surface of the Earth that runs from the North Pole to the South Pole. This is the International Date Line. For the most part, it follows the 180-degree meridian of longitude, but it deviates in several places to avoid dividing island nations or territories into 2 different calendar days. When you cross the International Date Line from east to west, the calendar advances by 1 full day. When you cross it from west to east, you go back 1 day. It is the internationally agreed-upon line where each new calendar day officially begins on our planet. The rotational speed of our planet, the very thing that defines the length of our day, is not a constant. It is gradually slowing down over geological time, a process driven primarily by the tidal friction caused by the Moon's gravitational pull. This braking effect is incredibly slight, lengthening the day by only about 1.7 milliseconds per century. But over the vast history of the Earth, this small change has accumulated into a significant difference. For example, during the time of the dinosaurs, a day was about 23 hours long. This gradual slowing will continue into the future, and to keep our atomic clocks, which are incredibly precise, in sync with the Earth's slowing rotation, a leap second is occasionally added to coordinated universal time. Our planet is not a uniform ball of rock and water. It is a rich and complex tapestry of different environments or ecosystems. From the lush, humid biodiversity of tropical rainforests to the cold, stark, and windswept landscapes of the frozen tundras, each ecosystem is a community of living organisms interacting with their physical environment. Each has its own unique set of conditions, such as temperature, rainfall, and soil type, which determine the types of plants and animals that can thrive there. This incredible diversity of ecosystems is what allows for the planet's overall biodiversity, providing a vast array of habitats for life to adapt to and flourish in. The story of life's long journey on Earth has been painstakingly pieced together through the study of fossils, the preserved remains or traces of ancient organisms. This scientific discipline is called paleontology. Paleontologists are like detectives of deep time, using clues from fossilized bones, shells, footprints, and even microscopic pollen grains to reconstruct what ancient organisms looked like, how they lived, and how they evolved. The fossil record, though incomplete, provides powerful and direct evidence for the theory of evolution, showing a clear succession of life forms over billions of years, and documenting the emergence of major new groups of organisms, from the first fish to the first land animals, and from the dinosaurs to the rise of mammals. The Earth's climate system is an incredibly complex and dynamic interplay of various factors. It is not governed by a single process, but by a delicate balance of inputs, outputs, and feedback loops. The primary driver of our climate is the energy we receive from the sun, but this is modified by a host of other factors. The composition of the atmosphere, particularly the concentration of greenhouse gases, determines how much of the sun's heat is trapped. The vast system of ocean currents acts as a global heat distribution network. The reflectivity of the Earth's surface, known as its albedo, determines how much solar energy is absorbed versus reflected back into space. Ice and snow reflect a lot of energy, while dark oceans and forests absorb it. All of these elements, and many more, are interconnected, creating a system of such complexity that it is one of the most challenging areas of modern science to fully understand and predict. A key component of this climate system is the greenhouse effect. This is a natural and vital process that helps to regulate the Earth's temperature and keep it warm enough for life to thrive. Certain gases in the atmosphere, such as water vapor, carbon dioxide, and methane, are transparent to the incoming shortwave radiation from the sun, but they are opaque to the outgoing long-wave radiation, or heat, that is radiated back from the Earth's surface. These gases trap some of this outgoing heat, warming the lower atmosphere. Without this natural greenhouse effect, the average temperature on Earth would be about minus 18 degrees Celsius, or 0 degrees Fahrenheit, and the planet would be a frozen, inhospitable world. However, human activities, primarily the burning of fossil fuels, have significantly increased the concentration of these greenhouse gases in the atmosphere, enhancing the natural greenhouse effect and leading to a rapid warming of the global climate. The challenges of this rapid climate change, along with other environmental pressures such as habitat loss and pollution, have brought into sharp focus the critical importance of conservation. The conservation of biodiversity and the protection of the environment are now recognized as some of the most significant challenges facing humanity in the 21st century. These efforts are not just about saving charismatic animals or pristine landscapes. They are about preserving the health and stability of the very ecosystems that provide the essential services upon which our own civilization depends. It is about ensuring that the planet's life support systems can continue to function for generations to come. This brings us to a final, overarching truth about our world. The Earth is a unique and precious planet. As far as we know, it is the only place in the universe that harbors life. It is a world of breathtaking beauty, incredible complexity, and profound history, and it is our only home. The responsibility for its long-term health and sustainability rests with us, its current inhabitants. Understanding our planet, appreciating its intricate workings, and recognizing our impact upon it are the first and most crucial steps in fulfilling that collective responsibility, ensuring that this vibrant blue marble continues to spin as a living world in the vast silence of space. And so, we return from the cosmic and the geological, back to the familiar world that surrounds us. The journey we have taken has not been across continents or oceans, but through layers of time and understanding, from the furnace of the planet's core to the thin, protective veil of its atmosphere. The solid ground beneath you is no longer just a static surface, but a piece of a tectonic plate drifting at the speed your fingernails grow. The air is not just an empty space, but a shield forged by ancient life. And the silent, steady passage of a day is the rhythm of a planet spinning in a precise and delicate dance with its slowly retreating moon. The 100 truths we have explored are not separate, isolated facts, but threads in a single, coherent narrative. The 4.5 billion-year biography of our world. It is a story of unimaginable violence and improbable stability, of immense, slow-acting forces, and the fleeting, beautiful phenomena they create. To know these things is to see the world anew, to understand that we are not merely living on the earth, but that we are a part of it. Our story is a fleeting chapter in its epic, and the future of that story is, for the first time in planetary history, being written by one of its own creations. The world continues its journey, and its story is far from over. Thank you for listening.